Thank you. Yes, I'm Kyle. I was a PhD student at MIT doing this work. I'm now graduated, but I'll tell you a bit about it. So I'll start by describing a bit kind of the target audience that we have here. So we have users who work in what we term extreme environments. These are high stress, high workload, and high risk situations. And I should say this is a bit different than some of the other talks we talked about because it has nothing to do with VR or consumer products and is highly theoretical. But these users might include disaster responders, emergency workers, search and rescue technicians, military infantry, and they all kind of have things that are in common. They must navigate on foot through their environments. They have to reach the disaster areas or find the victims or conduct tactical maneuvers. And something else that they also have in common is that while they're doing this navigation, they have to perform concurrent tasks. And this could be any number of different things, but more common ones are communicating on radios, engaging in combat, or trying to find targets. So traditionally, they've used visual navigation aids. So this has taken the form of the historic map and compass, pretty much out of date these days, but still used in the military context. As well as the more modern GPS display. On the right here, we have an example of what the U.S. military uses for their navigation display. It's a ruggedized phone, basically, that flips down from their tactical vest. But more recently, there's been a lot of work into haptic or tactile navigation aids. Most relevant to this work has been the research done by the U.S. Army Research Lab, where they are actually, I believe, deploying now into active use some of these belts that have tactors around them, and it vibrates in the direction you need to go. So if your waypoint or your place you're trying to go is on your left, it'll vibrate along the left side of your waist, and you follow that. So when we have different options of how we convey this information to our users, we now have to decide which option do we actually want to use. And so this brings us to the research question that I was researching, in that can we optimize the user's performance by adaptively selecting the modality that is used for a navigation system and changing it dynamically over time as the user's mission and context changes. So there are three considerations that go into this. First off, we have the inherent task-specific requirements. So depending on what kind of concurrent task your user is trying to do, there are constraints on what type of information you can convey to them simultaneously. So for example, if they are trying to engage in combat or trying to find combatants or search an area for disaster victims, that requires visual attention, as they can't simultaneously look down at a GPS display without being disrupted in their concurrent tasks. So if it requires visual attention, we have to use a haptic navigation system, or at least we should. Conversely, if their task requires haptic attention, so if they have to be able to feel the terrain beneath their feet or interact with something using their hands, or in the case of the haptic belt, the military is looking at using the vibration patterns to convey notifications such as chemical threats, then they can't as easily focus on the haptic sense for navigation, so we use a visual system. The second is the cost of switching modalities. So if we switch between a visual and a haptic system, the user gets confused. This is called a switching cost. They don't know where to expect their navigation cues from. And so that is a reason not to switch, or a cost to doing so. But on the other hand, there can actually be benefits to regularly switching between modalities. There are the effects of adaptation and habituation, similar effects in psychology and behavior, where a user's response to a repeated stimulus decreases over time as they become more accustomed to it. And if we can switch between modalities, it kind of resets that effect, and they actually get a boost in performance if they've become adapted to the old modality. So in terms of prior work, this is actually the conclusion of a three-phase experiment in a research project. So phase one, which was in IUI 2017, kind of focused on the cost of switching modalities, particularly in the haptic visual context. And what we found was that the switching modality of one task does not really affect performance on another. So while it decreases your performance within a given task, it doesn't negatively affect a different task. One of the other major results from that study was that you should not use a haptic source of information for multiple tasks at once, because it's very subject to interference and overload in that sense. Phase two, which was last year, was on the benefits of switching modalities. So this was specifically on the adaptation and habituation. And what we found here was that a single modality system, one that does not switch but remains consistent, fares worse over time compared to a switching modality system. But a single modality system will also have a better initial performance. So it starts better, but because it suffers from adaptation and habituation, over time there's a crossover point where it becomes worse. So this was phase 3, and this was taking all of this prior information as well as a lot of prior work on those task-specific benefits and trying to design and test an algorithm to adaptively select between the two in a navigation setting. So a bit about the design of the experiment that was conducted here. It was several months long of this past year. We had 32 participants and about 3 hours per participant. And because it was such a long experiment, we actually designed it as a horror-themed video game to try to keep participants' interest in it. And we had 3 hypotheses that we wanted to test, and they were that the adaptive modality selection will, 1, improve the navigation performance when there is no concurrent task, so they're just trying to navigate based on the fact that we can alleviate the adaptation and habituation. 2, that it'll improve the navigation performance when there is a concurrent task by avoiding conflicts between the two in terms of sensory input. And 3, that it'll improve concurrent task performance, so your performance on those secondary tasks, again, by avoiding conflict. So it's a little dark to see on the screen here, but they had to control an avatar in this virtual world, which was in a jungle at night. And they had to attempt to reach several different waypoints as quickly as possible. And the directions were provided either via a GPS display, as you can see here, which was designed to emulate, as I showed, the conventional military one, or a haptic belt, which you can see on the bottom here, which we built ourselves, very similar to the existing designs used by the military. And then they had to keep reaching waypoints until their time ran out. This is just a couple of photos of what the setup looked like. On the right, the virtual environment setup, and then on the left, someone wearing the tactile or the haptic belt. So the concurrent tasks that we used for this, we had 4 different ones that were designed to emulate tasks that, in this case, military users had to actually perform in their duties while they would be navigating. So the first was a visual attention task. They had to observe their environment and avoid certain targets. So in this photo here, you can see, it's hard to see, but the red circles outline different targets. Since it was a horror game, these are actually zombies walking through the woods that they have to avoid and not get too close to. The second was a hands-on task. So this emulates having to hold or maintain positive control of a weapon or other device. And here they had to not use their hands to manipulate the visual display so that they could maintain holding their device. The third was a haptic signal. This was based off of the Army Research Lab in the U.S. They are using the belt to convey signals, as I mentioned, chemical or CBRN threats. And the fourth being location knowledge. They had to be able to have an idea of where they were compared to their waypoints and be able to provide that information. So as I mentioned, these were based off of real-world tasks as closely as we could while maintaining kind of the immersion in the setting. So there were 4 different modes that we wanted to test through. There was the visual only, haptic only, multimodal, where both were provided at once, and then the adaptive mode. And this algorithm here shows how the adaptive mode worked. Simply put, if they needed visual attention through the visual attention task, or if they couldn't use their hands to use the visual display because they needed the hands-on task, then we used the haptic modality. Otherwise, if it was the haptic signal or the location knowledge task where they had to be able to look at the screen to know where they were, then we used the haptic modality. Otherwise, if they had been in a single modality for more than 5 minutes, which that number was based off of that second prior work that I mentioned, then we would switch between them in order to alleviate the adaptation and habituation. This graph shows the layout of the experiment. So on the top half, we have the different concurrent tasks that we provided to the user that they had to perform. And then on the bottom, this shows that as time progressed, how the different modalities would change. So in the visual mode, it remained visual throughout. Same for the haptic mode, haptic throughout. Multimodal was both throughout. And then the adaptive mode switched between them based upon which tasks they had to perform and if they had been in a single modality for too long. Looked at a number of different metrics, including the navigation speed, how quickly they're progressing towards the next waypoint, their bearing error, so how or what the amount of error was between the direction they are facing and the direction of their waypoint. the performance on those 4 different concurrent tasks I mentioned, and their subjective workload, as well as a Likert scale with several different items for a subjective rating. For analysis, we used linear mixed effects models for the majority of those, and then we looked at the comparison of the effects of the 4 different modes on each of those dependent variables, and then we used a Wilcoxon rank sum for the Likert items. In terms of analysis, the mixed effects models look something like this. I'm not going to go too far into the details of this for time constraints, but basically what we were looking at for hypothesis 1, the navigation performance, is we wanted to see whether there was a main effect of the mode when there was no concurrent task, or the interaction effect between mode and concurrent task when there was a concurrent task. For hypothesis 3, which was the concurrent task performance, very similar. Here, we just wanted to see if on the dv, the dependent variable of the performance on a given concurrent task, whether mode had an effect on that. Here we see the results. So the first hypothesis was not supported. In fact, the adaptive mode was slower and less accurate in the navigation compared to the others, with the exception of visual, when there was no concurrent task present. And this is simply because it appeared that the haptic and the multimodal modes were just quicker at navigation at a baseline level. Hypothesis 2, however, was supported. When we included a concurrent task into the mix, we see that there are a number of fairly strong effects ranging from 6.5 to 20-some% difference in terms of navigation performance when one of these other tasks was present. So what we see here is that this is comparing the adaptive mode to all of the others, and so this is showing that all of the others were worse than the adaptive mode for both the visual attention and the hands-on tasks. We couldn't test this for the remaining 2 concurrent tasks because by the very nature the participant could not move at that time, so it was impossible to measure their navigation speed. Hypothesis 3, the performance on the concurrent tasks was supported in some cases. You can see that compared to the adaptive mode, all 3 of the others were on average worse in every condition, and that several of those were significant, specifically for the hands-on, haptic signal, and location knowledge tasks. So what we pull from this is that the adaptive mode does really help, both on navigation performance and concurrent task performance when a user is trying to do both at the same time. On the subjective front, for the Likert items, we saw that the haptic mode was viewed as the best for navigation performance, subjectively. People just liked it because it was very simple to use. They didn't have to look at anything or try to interpret anything on a map. The visual was the worst for interference. They found that having to look at that screen was very interfering with the concurrent tasks they were asked to perform, and that the haptic modality provides very little location knowledge. So just based off those vibrations, it is very hard to tell where you are in the world in a global awareness sense. The implications of these were that, as I mentioned, if there is no concurrent task, you want to use a multimodal system because since you aren't worried so much about overloading their senses with multiple things at once, it is best to convey as much navigation information to them as possible at the same time. But if there is a concurrent task, the overload is a risk, and this adaptive system works very well. If you're going to use an adaptive modality selection system, you can expect that it'll improve your navigation performance in the presence of those concurrent tasks. It'll improve your concurrent task performance, but it is rated as more difficult to use. And finally here, I have a bit of a chart that kind of shows the summary of the results we had in this series of 3 experiments and papers, which provides a bit of a framework for if you want to implement a system like this in some sort of navigation device, some things you might want to consider. And it is a framework. It has to be customized to a specific application, but it gives an idea. If we have a navigation task, if it's of short duration, less than 5 minutes or so, then if you do not have concurrent tasks, then a multimodal system is best. But if you do have concurrent tasks, then you want to use the adaptive system based upon those task conflicts and trying to avoid those. If it is going to be a long duration, over 5 to 10 minutes of navigation, then if there are not concurrent tasks, we want to switch modalities every 5 minutes or so in order to avoid the adaptation habituation. But if there are concurrent tasks, then we use the full adaptive system that is based not only on the task conflicts, but also on the time in a modality. What that really comes down to is that a designer must prioritize. Do they want to they want to optimize for user preference, more likely in a consumer setting, or for pure performance, more likely in a military or extreme environment setting? In terms of limitations, it needs evaluation in a real-world environment. These experiments were all done in a simulated setting. It needs longer duration navigation. Users such as these will often be navigating for multiple hours at a time. Obviously, that's very difficult to do in an experiment setting since you need to do several trials, so that could be up to 10 hours of testing per person. And we need some variation in the concurrent tasks. We had 4 that were the same 4 we used for every participant to maintain consistency, but really, obviously, there's a very large variety of tasks users must perform in these settings, so we need to mix that up a bit. Some other things to consider in terms of future work are applications to non-pedestrian navigation, such as in vehicles, since what we studied was purely for people on foot, and also applications to non-navigation tasks. This idea of adaptively switching modalities over time can apply to a lot of things, such as different alert notifications or warnings in cockpits or other vehicles. Overall, as I mentioned, it's a framework. It gives an idea of where to go next or what to think about when we're applying such an idea to a different kind of system. That concludes the talk. I'll take any questions.
Thanks a lot, Kyle. That was very interesting. I wanted to ask a question. Maybe you said it and I missed it, but what was then the actual navigation technique that they were using? Were you using a treadmill? Were they using redirected teleportation? How were the users actually moving in VR?
So as I mentioned, it wasn't in a VR setting. They were sitting at a computer and using a computer game with a monitor. So the user themselves was not moving. They had to move their avatar in the game using a keyboard and mouse.
So how do you think that'd be different if they were actually physically moving? Because I guess it just changes like all your proprioception.
Yeah, I think the main difference would be the inclusion of all that haptic sensory input when you are walking and you are feeling the terrain, and that I think could throw off some of the conflicts. It could make some of the conflicts worse when you're actually getting all that extra sensory input and making you at higher risk of overload, in which case I think the system would perform better because it would really highlight the difference.
Mm-hmm. Okay. We have a question over there.
Hi there, Connor Soltis from Uber. Thank you so much for the presentation. I'm just wondering, in a real-world setting, how would you propose detecting whether there are concurrent actions going on or whether or not it's time to change modality?
That was a very popular question at my thesis defense, actually. It's not possible with all tasks, but it's possible with a lot of tasks. A lot of missions are, planned out ahead of time, and you have an idea of what is going to be happening, not just with time, but in terms of geofencing. If your user is trying to get into an area to surveil an enemy, for example, or to find a victim, you can tell when they enter the area where they're going to need to start doing that. That can be planned ahead of time. And with that kind of geofencing, you can switch between the tasks that they are expected to perform. Also, a lot of tasks that a user has to perform are provided in the form of orders or instructions from someone remotely who can provide that information digitally to the system, which would then be able to make the decision of whether or not to switch. Of course, there are situations where things change on the fly, and that would be a source of separate research, such as acoustic detection of gunshots or other ways to detect what is happening at the time.
Do you think there's a way to detect some of the other situations that you're describing, like when a user's hands are occupied, for example, or
when a user what? Sorry?
When their hands are occupied, or I can't remember. You proposed a couple other situations where you might want to change modality that involve like your hands are busy or your eyes are focused on a certain kind of thing.
I think a lot of those are directly connected to what kind of tasks they're performing. If they're in an area where they do need to be, again in the soldier example, ready to engage a target, their hands will always be occupied with maintaining control of their weapon. I'm trying to remember what the other one you said was.
Oh, got it. No, I think that answers both of them. Thank you.
Yeah. Sure.
Okay, thanks a lot. So, well, I would ask to maybe thank our speakers again. So, with this, we finish our session on navigation. Thanks everyone for being here. And please remember, if you like the talks that you saw, remember to vote for